Examples of computer-aided design problems using voxel geometric models. Consider the problem of placing additional equipment in the technical compartment of the vehicle, the problem of pre-assembly. This problem is often found in the practice of design and from a geometric point of view is reduced to the problem of analyzing the geometric shape of empty spaces among previously placed objects. We will solve the problem of additional placement in the following statement: there is a closed area, for example, the technical compartment of the aircraft, with the equipment already partially placed in it. A. There is a set of equipment that needs to be repositioned. B. The possibilities of additional placement are determined by the shape and size of still unfilled spaces between already composed objects. Technical compartment of the aircraft. A. Redeployable and equipment. B. For a person, such a task rearrangement of objects will seem quite easy. He can easily by eye determine how several volumes relate to each other and which object fits in another and which does not. To do this, he mentally classifies the object by shape, almost a ball, almost a cylinder, and then mentally correlates their sizes. Unfortunately, this operation of pattern recognition, which is so simple for a person, is of considerable complexity even for modern computers. The most important issue is the class of geometric objects allowed to be placed. Typically, from a geometric point of view, such equipment is either primitives or a combination of primitives. Assume that the objects to be placed are a composition of primitives that describe the shape of the instrumentation quite well. This can be seen in B. The technical literature provides data that the composition of primitives effectively describes 95% of the instrument equipment. The advantage of the voxel geometric model is the ability to identify empty spaces in the layout for subsequent placement of objects not yet placed in them. If there is an empty space among the assembled objects, then on the corresponding section of the voxel matrix it is relatively easy to identify as clumps of zero voxels. For this purpose, an algorithm was developed to determine the center of a certain free area, flat, and its dimensions. To do this, scan the rows and columns to identify the largest cluster of inextricably located receptors and identify their centers. To analyze the individual cross-section of the object, we use the transition from the geometric shape of the object, in the form of a discrete set of receptors, to the feature space adopted in the theory of pattern recognition. Such a feature space for us will be the hodograph of the function of the radius of the vector from the center of the section. Construction of the hodograph of the radius vector function, A, and analysis of the unfilled area of space, case polygon, B. Where res the current radius vector length for the I receptor and phi is the current radius vector angle for the ith receptor. After constructing the function re phi I, its analysis begins. If the shape of this region were a circle, the function would be an ideal straight line whose height would show us the radius of this circle. B. If a regular polygon is a saw with the number of vertices equal to the number of sides, the coordinates of the vertices on phi will determine the aspect ratio of the rectangle. To do this, we use the method of testing statistical hypotheses, implemented as a computational software module. On the real results of the analysis of the hodograph function, naturally superimposed noise due to the discreteness of the description of the component objects. An example of such real hodographs of a plane slice of the objects being assembled, statistically identified as slices of polygon, cylinder, and sphere, are shown in A, C, respectively. View of the hodograph of the slice function from for the polygon, A, sphere, B, and cylinder, C. An illustration of the software implementation of this method is presented in. The obtained results are implemented in the framework of a graphical shell written in C#. If we have a desire to place in this area not a parallelepiped of the maximum size, but, for example, a sphere of a certain radius, then it becomes a full participant of the scene, and after pressing the analysis button, a new definition of the configuration of unfilled spaces occurs. Determination of the configuration of empty spaces, A. Visualization of space, B. Output of data on the size and position of the free area, and, C. Assessment of the possibility of inscribing different shapes. The solution of the task was carried out within the framework of the dissertation research by Sichu Lin, Republic of the Union of Myanmar, a postgraduate student of mine described in. The purpose of designing the channel surface is the delivery of a certain trajectory of a material carrier, liquid, gas, electrical energy from one point, entry point, of the technical product to another, exit point. In this case, one of the tasks of the layout is to solve the problems of tracing, i.e., designing communications between already placed objects. Such problems are quite difficult to formalize and difficult to solve because of their inherent multi-extreme nature. A special and much more complex type of trace is called solid trace, that is, such a case when the dimensions, connecting elements, of the trace are comparable to the dimensions of the components. In practice, this is the design of pipelines, air ducts, and other elements of transport systems. An example of laying the trace: A. Electric furnace and B. The air duct channel of the car. To solve this problem, two main approaches to tracing are used, which are determined by the metric used. A metric is a rule that determines the distance between 2 points in a given space. The first approach is to use the Euclidean metric. In this case, the trace is drawn in the direction of the shortest distance between the entry and exit points, A, and the length of the trace is determined by the Pythagorean theorem. Designing trace with different metrics. The second approach is to use the Manhattan metric, in which the trace is drawn in the direction of the coordinate axes, V. In this case the trace is much longer than using the Euclidean metric, but the approach itself provides additional mathematical possibilities for the design of the trace. It is used for tracing large integrated circuits and printed circuit boards. This metric is used by industrial automated tracing systems PCAD, R, and others. A typical example of the result of wiring in such programs is shown in C. From this figure it can be seen that the tracing in such systems is carried out either by the Manhattan metric or at 45 degrees angles. In our opinion, the problems of trace design according to the Manhattan metric are the most developed in the theory of geometric modeling of traces. This is due to the extreme practical importance of solving these problems in the automated wiring of printed circuit boards and large integrated circuits. Fundamental in this field are the theoretical studies of Russian scientists Abrades Pound, Vasilovich R.P., Petrenko A.P., Tatalbaum A., Salyutina V.A. and others, as well as foreign scientists U. Dijkstra, Judea Pearl, Ira Pohl, Daniel Delling, Peter E. Hart, etc. However, the use of the Manhattan metric is unacceptable for channel design, since due to viscous friction, the sharp bends of the channel make it difficult to move liquid or gas through the channel, turning the flow energy into heat. The current line that determines the direction of travel through the channel is called the main guide line, GNL. It is the axis of the channel and is given either by the equation of the spatial curve or by a discrete set of points. However, tasking this parameter alone is not enough, it is necessary to specify the shape and area of individual cross-sections of the channel. By controlling the position of the GNL in the shapes and sizes of the cross-sections, we can provide the specified designer characteristics of the flow of liquid or gas through the channel. Geometric parameters that determine the shape of the channel. Let us complicate the task of designing. If earlier the channel was first designed according to the specified characteristics and then it was already placed, then we are trying to design a channel with the specified characteristics, inscribed in an already existing layout. Let there be a rectangular area with dimensions x times y, in which the areas of prohibition are located. The entry point A and exit point B of the channel are specified. It is necessary to draw a trace between the given start and end points A and B. Obviously it is that in such a statement the problem does not always have valid solutions. Finding a rational path between two endpoints A and B in a 2D formulation without taking into account the size of the trace and the restrictions on smoothness. From it can be seen that there are quite a lot of options for its passage. At first glance, of all the traces in, the one that is shorter will be better. However, it is known from design practice that hydraulic losses are minimal not in the short but in the main channel. Additional requirements are possible, for example, to provide a specified gap between the channel and other elements of the layout.